I have actually uploaded these recordings on YouTube, but I forgot to share the links with you guys. But I've shared the links with Aero Lab 1 students. So if you go on Blackboard, you will see the YouTube links of the recordings. And yeah, so we have already talked about thermodynamic laws, first law and second law. It was just a review, if you recall. And we are going to start talking about power cycles today. But before talking about power cycles, let's talk a little bit about your homework 1. Your homework 1 is going to be, was supposed to be posted on Wednesday, and it was supposed to be due in a week. It is still due in a week, but I received an email asking me to post the homework earlier. I will try to do this. It is not going to change the due date, so essentially you're going to have more time. But I haven't designed the homework yet, and I will try to post it today, either today or tomorrow. But I'm sorry if I couldn't, if I didn't have the time to post it earlier than it was scheduled. And your homework is going to be essentially based on the thermodynamics, the power cycles, and the review of thermodynamic laws. And you will probably get, you will definitely get 4 to 5 questions covering all of this. And then we will move on to the propulsion part of it is still thermodynamics, but with more focus on jet engines, essentially. So we are still going to do the same analysis. It's just a different name. Any questions about the homework, about the anything? Okay. So let's do this. I'm sorry. I don't know what happened. What happened? So we're going to talk about power cycles. The first question we need to answer is, what are power cycles? To be able to answer to this question, you need to understand what are thermodynamic cycles first. So is there anyone who can tell me what is a thermodynamic cycle? So 2 questions. First, can you tell me what is thermodynamic cycles? And second one is, did you go over thermodynamic cycles in your Thermo 1 at all? A little bit. So what are the thermodynamic cycles? You dug the hole for yourself, right? Anyone? No one?
Like a Brere cycle or whatever?
What is a cycle in general? So if you recall, the thermodynamic process was like going from point 1, state 1, to state 2. This state 1 has a specific energy, state 2 has another different energy, lower or higher energy, right? Through heating, through work, through whatever. That's the thermodynamic process, right? When you come back to state 1 through other processes, this is called a thermodynamic cycle, right? So, pretty simple. So we understand what thermodynamic cycles are, but now we want to understand what power cycles are. Essentially, power cycles are cycles in which we generate power, right? We use heat mostly, right, to generate some sort of power, right? A mechanical power or whatever, or electrical power, electricity, like in turbines, in power plants, right? And so on and so forth. Any questions so far? So the topic of this power cycles is essentially going to be the generation of this power generation. What are the type of cycles we are going to deal with in this course in thermodynamics in general? There are 2 main power cycles: vapor-based power cycles and gas-based power cycles. So this vapor and gas refers to the working fluid of the cycle. So essentially the process is like this. You usually heat up a gas or a liquid, a fluid in general, and then use that higher energy gas or higher energy vapor essentially to move something, to move a turbine, to move something, right? Whatever that is, right? And that's vapor or gas is called your working fluid. That's the thing that is going to circulate inside your system. Yes?
I think I could be remembering wrong, but I think I remember some parts of the journal where we talked about reversible cycles.
We talked about reversible cycles or reversible processes. We talked about reversible processes last week, right? You remember that?
I think so, yes. Can that kind of same concept apply to the power cycle? Even though it'd be like
So let me ask you this. What is a reversible process?
It's like it's with the graphs where it moves from like state 1 to state 2 and then go back to the previous state. Am I thinking of that correctly?
Can you repeat what you said? I didn't hear you correctly.
Like where we had like a Carnot cycle, something like that, where it had state 1 and then 2 different point on the graph, state 2, state 3, state 4, something like that.
So what is the difference between a Carnot cycle or any cycle in general and a reversible cycle? Because that what you said is just cycles, right?
I can't remember.
Okay, who can tell me what a reversible process was? A reversible process.
So it was isotropic. There's no loss of energy.
Don't mix isentropic with reversible. Isentropic is a little more, I think it's a little more limited, right? Because isentropic processes are reversible and adiabatic, right?
What's the net change in entropy? Zero?
Changes in entropy is zero, right? As Igor and Drew, right? So So reversible process, where you go from 1 to 2, your delta S is 0. This is a reversible process, right? In a cycle, you go from 1 to 2 to 3 to 4 to 1 again. So yeah, definitely delta S in an ideal cycle must be 0. So because you are going back to a state 1, right? But reversible only talks about the entropy. So between 1 and 2, you may have temperature change, you may have enthalpy change, whatever. But your entropy doesn't change. That is the thing that doesn't change, right? So make sure you don't mix these two things up. Yes?
Power cycles aren't reversible though, right? Like in terms of like the vapor power cycle, you gotta steam it. You can't just run that in reverse.
We don't really define. My point was we don't really define reversible for a cycle, right? It is a cycle, right? So a cycle can have a couple of reversible processes included in it, right? Which reversible processes don't really happen in the real world, right? Does this make sense? So make sure not to confuse these two. Okay, so where were we? Power cycles. Okay. So power cycles are cycles that use vapor or liquid in general that turns to vapor, that changes its phase to vapor as working fluid, and gas cycles are cycles that use gas as their working fluid. Can you give me an example of a gas cycle? So your working fluid, the fluid that you are heating up and extracting energy from, is gas. Can you give me an example?
Internal combustion engines.
Internal combustion engines. What else? And what is the working fluid in an internal combustion engine? it's air mixture, right? It's air gas mixture, whatever, gasoline mixture, right? The air part of it is very important. What else?
I might be thinking wrong, but natural gas engines?
Yes, natural gas engines, but the natural gas engines are essentially internal combustion engines, right? They're the same thing, right? That is true, though. Any other example? Jet engine, right? We're sitting in a propulsion class, so we are actually, I would assume the first example that comes to your mind is a jet engine. Jet engine, what is the, yes?
What about like liquid fuel engines, like with rockets, where they oxidize?
Liquid fuel engines or rockets, liquid fuel rockets are not cycles, right?
Oh, yeah, that's a good point.
You only go back to the original state. But when you are dealing with a jet engine, you have ambient air coming in, and then ambient air, you exhaust to the ambient air. So that's your cycle. Yes?
I'm still confused about the difference between vapor and gas, because when did you consider those to be like air, gas, vapor? Or was there just air?
Air, gas, vapor.
Right, it's like gas vapors, I guess, instead of.
So whenever you are dealing with vapor, whenever you're talking about vapor, you're talking about, always think about a liquid gas mixture, right? Or vapor quality. You remember vapor quality from your thermo, right? So whenever you are dealing with vapor, it means that there will be some phase change.
But these are all
From-
vapor engines?
These are all gas engines, so there is no phase change from
Oh, okay.
air doesn't become liquid, right? Air. That's why I said air gas mixture. Air is the most important part of the cycle here in an ICE, right? You only use the gasoline for the combustion, for the heating part of it. Okay? Does it make sense?
Yeah.
Okay. Well, what about the vapor? So essentially, you had a question too, right?
I was going to say ramjet, but I think that's jet engine.
Ramjet, yeah, exactly. Ramjet is also jet engine. It's the exact same thing, and actually, ramjets are a better representative of this. I mean, we'll talk about this. Let's talk about vapor. So I assume you can conclude from the discussion we have had that our focus is going to be mainly on gas power cycles, right? But we need to, as engineers, we need to be familiar, as aerospace engineers. But as general engineers, we need to be familiar with vapor power cycles as well. Can we think of a specific vapor power cycle? A steam engine. Exactly, a steam engine uses steam, right? So essentially you boil up some water up, right? Some liquid water, you generate steam and use that extra energy that you have given to the steam to move a piston, right? That's the idea, exactly. Thank you.
Thermic centrals, like thermic centrals, like they produce energy, electricity by steam power.
Can you repeat your question?
Like, can thermic centrals, like, you know, they boil the water with, actually they use fusion of nuclear energy, but they use steam, they boil the water, they use the steam.
It doesn't matter how you boil the water. You can use like the geothermal plant, nuclear plant, doesn't matter how you boil the water. As long as working fluid inside that cycle that generates the electricity is water, liquid, that turns to vapor, you have a vapor power cycle. Okay? Does that answer your question? So that your example is correct, right? So let's go a little deeper in the vapor power cycles first. And we are going to mainly focus on vapor power cycles for this lecture, but then for next lecture we are going to, hopefully we'll be done. We'll finish the vapor power cycles today, and then we'll start the gas power cycles. We'll talk a little more about them. Yeah. Okay. So vapor power cycles, the main vapor power cycle is called a Rankine cycle. Have you talked about Rankine cycle in your Thermo 1? No? Okay. What is a little bit though? Can anyone elaborate on a little bit? Name sounds familiar. Okay. Okay, that's so you haven't talked about it. Who taught you thermo? Who did you have your thermo with? Cyrus. Who has Cyrus? Who had Tony? Dr. Reynolds. What about the others?
I had Greenberg.
Who?
Greenberg, he was a
Greenberg?
He was a graduated master's student who they brought back to.
Ah, you're talking about Ben.
Yeah.
Okay.
He talked about it. I just have to
He
remember
did.
the 2000
But
still.
There's so much more to get through that you didn't really get through anything.
No, that's all right. We are gonna talk about it.
I know he talked about it.
Yeah, we definitely mentioned it, but
I remember.
Yeah, he was actually my aerodynamics student. Nice guy.
also along to
Yeah,
But let's get back to the lecture, guys. Let's get back to the lecture. You guys go off topic very fast. Okay, so in a Rankine cycle, we are going to have a boiler in which we boil a liquid. Mostly, like in power plants, we are going to use water. Water is the most common, like working liquid, and this boiling can be done in a nuclear reactor. It can be done in a gas reactor, in anything, right? The boiling process is the thing that is going to change the power plant, right? The rest of it, the turbine, is usually very similar in different power plants, right? And this boiling, and this part of the process is state 1. Then you go to a turbine. After the turbine, you have a state 2. And in this process, your gas has expanded, right? Your vapor has expanded and lost some of its energy, right? And then we are going to have a condenser. People use different shapes for condenser, but this book has used this shape, which your gas is going to change phase to water. So after condenser, we want to have saturated liquid water, your vapor. And then it is going to pump back up into the boiler, which is going to be the state 4. So this is going to be the main schematic of a Rankine power cycle. So we have power output of the turbine and power input in the pump. We need to be able to pump the water back into the boiler, and we're going to extract some work out of the turbine. We are going to assume turbine's process is isentropic. That's the assumption. So what does this mean? When we say turbine's process is isentropic, what does this mean?
Entropy is 0.
Entropy is not 0. Changes in entropy between a state 1 and state 2 are 0, right? So S1 is equal to S2. It is at the reversible part refers to the entropy change. And what does adiabatic mean? Q dot is 0. So we are essentially assuming that there is no heat transfer and there is no entropy change, right? So what does it mean for the work extracted from turbine? How can we calculate this? Based on the first law of thermodynamics, if you recall, we said delta E is equals to W minus Q, right? Q is 0. Delta E is going to be equal to the amount of internal energy change plus the kinetic energy change plus the potential energy change is going to be equal to turbine's work. this internal energy change is going to be equal to m dot H2 minus H1, right? The changes in internal energy is essentially equal to the changes in enthalpy, right? Right? And we can actually neglect kinetic energy and potential energy. And this is a slide I have on my presentation as well. If you calculate the changes in kinetic energy and changes in potential energy and compare it to the changes in internal energy, in this type of processes, you can see that changes in internal energy is like 1,000 times higher. So we can safely just say these are 0. So the power output of turbine is going to be equal to m dot H2 minus H1. Okay? Yes?
Why do we have the derivative of work and the derivative of heat? There's power.
That
Watts.
So this is the rate of change of energy over time, right? This is actually delta E divided by delta T. Thank you for the correction. Delta U divided by delta T. Pardon me?
Aren't W and Q also with respect to T?
Whenever you see this dot on top of something, that's the rate of change over time. So W itself is work, the rate of change of work over time is power, right? And we usually deal with power here. We don't really deal with work. Any questions?
One last thing.
Yes.
Isn't energy heat minus work minus heat?
I'm sorry. That really shouldn't change anything. Yes, you're right.
Would that make the work negative in that case?
No, so that doesn't really no. So again, go back to the definitions we had. Negative work doesn't really exist, right? When we say negative work, it means that the work is done by the system, not on the system, right? So that's just a convention, right? I mean, whenever I make this mistake, bring this up, because we need to be consistent, but we are not going to be wrong if we just choose a different value, right? It's just the convention is going to change. But we need to have a consistent convention, okay? Okay, so let's continue. Let's go to the condenser. So based on this analysis, the idea here is that in the condenser, we are going to condense the vapor, right? So we are going to remove some heat. The goal here is to generate some saturated liquid at state 3. But the question you may ask, or I'm going to ask you this question, is that why do we need a condenser? Because we have spent this much energy boiling water to vapor, and then we have extracted some of the energy out of that turbine, inside the turbine, right? So it is a lower energy, vapor quality is going to be lower, but then we are going to waste the rest of that energy in a condenser. Like if you're going to have some Q out, we are going to remove some of it. Yes?
Would we have a higher concentration of power output?
Higher concentration of power output. But that condenser part doesn't really contribute to the power output, right? Yes?
Is it easier to pump a liquid?
Exactly. It is basically the only way to do it. You want to pump a liquid, you don't really want to pump vapor, because your pump is going to either it has to be a very special kind of pipe to be able to count the vapor, right? So we need to remove the excess heat from the vapor and bring it out to a liquid state. We are removing some heat, and we are going to assume that there is no work done on this process, done on the system or by the system, doesn't really matter. But how can we calculate the heat? Q dot here, again, based on the first law, Q dot is going to be m dot equal to m dot H3 minus H2. Just to be consistent with the previous sign convention, we are going to do H2 minus H3. So it gives us the same convention. Okay. The next part is going to be the pump. That's between a station 3 and a station 4. Pump. We are going to put in some work here. So work is done by the environment on the system, right? To be able to pump the water back into the boiler. And that is going to be, can be calculated using the first law again, m dot H4 minus H3. And this is Q dot of condenser, or also Q dot out. No, just because we wanted to remain consistent with the sign convention, it should be H2 minus H3. And Q dot in, or Q dot of turbine, that is going to be between a station 1 and a station 4. It's going to be m dot H1 minus H4. So these four equations are going to be your main equations. That are going to help you analyze a Rankine cycle. But the problem is going to arise when you need to find the enthalpies at different. That is going to be the hardest part, like finding the enthalpies at different states. Right? You have to be able to use the thermodynamic tables or the NIST web book. Is there anyone who is familiar with the NIST web book? No? Okay. I guess we can go over that as well. But you don't really need it because, yes?
Do you always need a condenser, or can you just have like a large reservoir as well?
What does a large reservoir gonna do?
Huh?
What does it gonna do? What is it going to do? So you essentially put the water back into a reservoir and then pump it into the boiler, right?
From like the bottom of the reservoir, so it's cold.
As long as it is in saturation condition. But what are you doing to that vapor that is coming out of the turbine? Aren't you cooling it down?
Oh, so the issue is it just collects there?
That reservoir is your condenser. As long as you are cooling down the vapor with a solution, doesn't matter what your solution is, whatever your solution is. Condenser is just the name, right? For the process of condensing the vapor. Yes?
Well, I'd be confused on the orientation of the H's.
Okay.
So why is it 2, 3 in that case? Would it be 3, 2 like we had originally?
Okay, so we have delta U. Delta U is equals to Q dot minus W, right?
Yeah.
That's right, that's the correct convention, right? So if you have, let's say for your m dot is H1 minus H2, right? For the first turbine process, equals to negative W dot. We don't have any heat transfer, right? This is going to change the signs, right?
Oh, okay.
But for the next one, if you want to remain consistent, you have to do H2 minus H3, right? Equals to Q dot minus W dot. This time it's 0. So this doesn't really change its direction, right? Does it make sense now?
Yes.
Are you sure? You don't look convinced.
I'm more
More convinced. That's a step in the right direction. That's good. That's good. Okay. So, there are a couple of things that we need to introduce here. And the first one is the thermal efficiency of the cycle. Efficiency of the cycle. So, the idea here is that we put in some heat and we get some work out, right? Based on this idea, how can we define the thermal efficiency of the cycle? Think about it. The idea here is we want to put in some heat to get some work out. Based on this idea, how can we define the thermal efficiency? Heat change. I'm not looking for an equation. I'm just looking for the definition. How would you define the thermal efficiency here? Yes.
Work in minus work out.
Work in minus work out minus work, right?
Work out.
As the goal is to get the work out, right? And that's it. That is going to be the net work, right? That's it. So that net work is your thermal efficiency? Yes.
Wouldn't you divide like the amount of heat in by the work out?
That's it. So that you actually the other way around, because the goal is to get the work out. So thermal efficiency of a cycle is going to be equal to the power output divided by Qn, right? And power output here is that the power of turbine minus the power that is wasted to pump the water back into the boiler divided by Qin. How did we find the power of the turbine? H1 minus H2 multiplied by m dot minus m dot H4 minus H3 divided by H2 minus H3, right? Divided by H1 minus H4 multiplied by m dot. If you play with this a little bit, you can take the m dots out, and you can actually have an H1 minus H4. You can take that out as well. You're going to get to this equation: H1 minus H2 minus H3 divided by H1 minus H4. Okay, so this is going to be your eventual way of calculating the efficiency, or you can actually use this equation. That's probably going to be more useful because in all of the examples you will end up calculating the work before calculating the efficiency. So we know how to calculate the efficiency. There is one more thing that we need to talk about. We talked about the net work. The total work that is out of the turbine is equals to Q dot in minus Q dot out, right? Just have to keep that in mind. And also we have another concept, back work ratio, which is going to be WBR is W dot of P divided by W dot of P, H4 minus H3, H1 minus, why do I have H1 minus H4? I think I messed up the signs here. I have to double check the signage on the turbine worked out. But on my notes, I have H1 minus H2. So just make sure you correct this for the time being. Yes. H1 minus H2. And anyway, keep in mind that the signs are just a convention, right? It's not a real. The delta H is the more important part. And you are not going to deliver negative work out of the turbine. Negative work out of the turbine is going to mean that you are going to rotate the turbine shaft yourself, right? With an external engine. Does this make sense? Okay. So, let's actually solve an example. Let's see, I think we are ready for an example. Yeah, let's do this. And this, let's actually treat this as a quiz, as one of the random quizzes you are going to participate in, you are going to take.
What's the last bit about BWR, please?
Let me bring up the this is an example in the Moran book, the thermodynamics book. And this is the example. So we are given, do we have the thermodynamic tables? Is there anyone who has the thermodynamic? No one. Okay. So keep in mind, that's a very good thing that he brought up. Thermodynamic tables are going to be very important in this course and in any thermo-related course. Right? I guess you can use your laptop, whatever, cell phone, whatever you have, or I can give you the numbers. That's it. So we have steam, which is the working fluid, in an ideal Rankine cycle. Saturated vapor enters the turbine at 8 megapascals. And saturated liquid exits the condenser at pressure of 0.008 megapascals. The net power output of the cycle is 100 megawatts. We want to determine the thermal efficiency, the back work ratio, and all of those nice things. So the first thing you want to do is to calculate the enthalpies based on whatever that is given to you. We have the saturated vapor entering the turbine. So we have the state 1's pressure, and that is saturated vapor, right? And we also have saturated liquids as it exits the condenser. So a state 3. And the only other clue we have here is that we need to look at the saturated tables, saturation thermodynamic tables. Okay? Since we don't have any thermodynamic tables, I guess I can give you the numbers, right? Just ask me what number do you need from the table. What is the number you're looking for? What is it like? Yes. Q in. That's something you need to calculate. What do you read from a table? That's a very good question. What do we read from a thermodynamic table? Let me actually see if I have the. I do have the PDF for the book. You want to find the enthalpy. Enthalpy is one of the things we read from the thermodynamic tables. All right, here. So you come to this book, which is the one of the textbooks of the course, and we actually have the same thermodynamic tables in the other propulsion book. You come to the indices, right? Yes. And look here, properties of saturated water, pressure table. We are given the pressure. We want to look for the properties of saturated water. Okay, let's click on this. It is not clickable, so I'm just gonna table A2, A2, A3, right? So what is the pressure that is given to us? 0.008 for liquid, for the liquid one, right? So 0.008 megapascals, right? What was it? So you have the numbers here, right? Which row are we looking at? How can we convert bars to pascals?
Something with T.
Not 3. But I mean, Igor was right. So 1 bar is 10 to the power 5 pascals. Okay? So 0.008 megapascals. 0.8 bar, huh? That's it. So this is the value we want to look at. This is right here. We use it just for the recording. This one, right? And you'll probably get this saturation condition at 90.93 degrees Celsius. And what are we reading here? Saturated liquids enthalpy. Is this the only thing we need? Yes. You had a question?
No, I was just trying to find
This line. This line, right? That's 0.008 megapascal. That's 0.020, so 0.08 bar right there. You're right. Sorry. This one, yeah. So what are we trying to read from this table? The first one is, of course, it's enthalpy. At enthalpy, you have saturated liquid. It's going to be your H3. Okay? That's the enthalpy at the state 3, after the condenser. Okay? Is this the only thing you want to read from this table? What is the other thing? Yes. Do we have any saturated vapor at the station 3? We do have it at station 1, right? So, but at this state, for a state 3, at the station 3, what else do we need? Keep in mind that we are dealing with isentropic processes, right? So we can actually use that to our benefit. What was the definition of an isentropic process here?
Are we going to use internal energy?
I don't see how you are going to use the internal energy, but it's probably not a bad idea to check that as well, right? But I'm specifically talking about entropy, right? Because, right, what happens in a turbine is an isentropic process. The same is true for a pump. So if you read the S3, if you read the S3, you essentially have the entropy at the station 4 as well, right? Does this make sense? Let me actually go back to this drawing of the Rankine cycle. Why doesn't it work? I hate this software. Wait. This one. So we said this process is isentropic, this process is also isentropic. So if you have the entropy at the station 1, you have the entropy at the station 2. If you have the entropy at the station 3, you have the entropy at the station 4, right? So it's probably not a bad idea to record the entropy as well. So let's do this, the same table reading for the other part of it. We had, what was it? It was 8 megapascals, which is going to be 80 bars, right? Very high pressure. 80 bars. It's going to be this line, right? So, let me actually. Can you read the numbers? I guess so. Again, we want to record the entropy as well as the enthalpy. But this time we are dealing with saturated vapor. So we are going to record H of G and S of G.
What was the pressure? Sorry.
80 bars. So 8 megapascals, which is 80 bars. Okay, so we have the enthalpies, we have the entropies for one station. What should we do next? Do we have any information about the other states? H1 equals to, so you are saying that the W dot of turbine is equals to W dot of pump. Who said this? Oh, is it you?
Yeah.
Oh. So, but if they are equal, then there is no net work output, right? They are not. They shouldn't be equal.
100.
What's that?
100 goes in this.
So that's okay. So you are saying, what you are saying is that W net is net power output is 100 watts. So WT minus WP, W dot T minus W dot P should be 100 watts, right? 100 megawatts, whatever the number is. Okay. What can you conclude from that, though?
To know what the mass flow rate is.
What's that?
You wanting to know what M dot is.
I didn't hear the question again.
Like, so to find.
You don't know what M dot is? Is that your question?
Yeah.
That's the mass flow rate.
Yeah.
But this is something we need to calculate. So we are at an impasse, right? It looks like it. Do we have any solutions to go any further?
Can we go back to the question?
Sure. Where did it go? That's it.
Use of the efficiency equation, 1 minus H2 minus H2.
Let's actually do this. Whatever idea you have, work on it a little bit. I'll give you 5 minutes. Just work on your ideas, and then we'll come back. Okay?
Is this the same setup as what we have in notes? As far as like the configuration of the system?
What's that?
Is the system in this like problem the same configuration that we had in the notes where it's boiler turbine?
Yes, yes, yes. That's the Rankine cycle. That's a closed cycle.
Okay.
I got confused. We still don't have H2.
Don't have H2 and H4. That's correct. And this is what we want to count. We want to find. So your goal here is to find a solution to find H2 and H4. I guess something that may help you a little bit is the TS diagram. Okay. We'll definitely use another software. So TS diagram. We are operating inside the saturation condition, right? That's the idea, right? For the most part. So we have the state 1 here. Then we are going to lose some energy in the turbine. The state 2 through an isentropic process. Then we are going to lose some energy to a state 3 through an isothermal process. Means that the only thing that changes is your phase, right? You're going to lose some vapor quality. Then you're going to have some energy into the pump, and then you're actually, this is the process inside the boiler. We are going to increase the temperature until it reaches saturation condition, and then let me ask you this. Do we know what the TS diagram is? This is, I'm pretty sure you have seen this in your thermo. That's,
Yeah.
yeah, you should definitely. Yes. So what is inside this? Inside this. What is happening inside this? You essentially get to the saturation condition, right, as liquid, and it goes to vapor. So this is here when you are changing, your vapor quality is changing. You are inside the saturation condition. The reason, what's that?
It just like with the different regions.
Yeah. So essentially, I guess we need to explain it a little more. At station 1, we are after the boiler. We have saturated vapor. Vapor quality is 1, right? You remember vapor quality from thermo 1? No. We have 1 no. Is there anyone who doesn't remember vapor quality? 2. Don't be ashamed. I mean, if you don't remember, that's all right. Because we are going to use this. If you don't tell me you don't remember it, then you will have some problem during an exam, right? That's for sure. definitely you will have a lot of problems during an exam. So vapor quality is essentially the amount of vapor present in your saturated system, right? So here, this is the critical point. If you recall, we talked about this a little bit, right? On this side of it, we have saturated vapor, right? Which means that the vapor quality is 1 because everything you have is only vapor, right? On this side of it, where we have liquid here and we have vapor here, right? We have gas here actually. And we have liquid vapor mixture here. So when we say vapor quality as 1, means that all of your system is vapor, saturated vapor. So this is the case at the station 1, right? Just after the boiler, we have boiled it up to a saturation condition for saturated vapor. Then we send it into turbine. It loses some of its energy, right? Which means that you're going to have some expansion. Temperature will drop. See this process? Temperature is dropping, right? And also what is happening here is that some of your vapor, this 100% vapor, is changing its phase to liquid. So at this location, since we are inside this, right, your vapor quality is going to be like 75%. What does it mean? It means that 75% of that working fluid is a still vapor, of that mixture is a still vapor, and 25% of it is liquid, right? As you go closer to this line, your vapor quality decreases, which means that more of your mixture is going to be liquid, right? Whenever you have trouble imagining the vapor quality, think of an ice-water mixture. Right? Your ice water, it doesn't really matter how much ice you have in your system, it's always at 0 degrees, right? If you remove some heat from it, if you put it in a freezer, the amount of ice in that mixture is going to increase, right? So that's essentially the same thing here. The amount of vapor is increasing or decreasing. And the amount of vapor in the system, the fraction of vapor in the system is called the vapor quality. Right? Okay? Is this clear? Okay. So for a system like this, and we have for this one we have, what is the pressure here? 8 megapascals. For this one here we have 0.008 megapascals. Okay. So whatever you didn't know, you should tell me, right? If you don't, I don't know you know things or you don't know things, right? I'm not in your head. You should know me. You should tell me. If you don't tell me, it is going to be to your. I guess you're gonna have. You're gonna have a tough time in an exam. And it is all right if you don't know. Sometimes I don't know things. Sometimes I mess things up. We are people, we may forget things. We may have not studied well. So there is no shame in not knowing things. No shame at all. So let me do this just to make sure that next time you do this earlier. Who were the guys who said they don't remember the vapor quality? It was Steven, Kareem, and Emery, right? Just the three. You will get bonus points for like being, I guess, brave enough. Just remind me if I didn't give you bonus. But this is very important to me. That's why I'm focusing on it. If you don't know something, you have to ask. Okay? Okay, so where were we? Okay, so, and I said under this, whatever you want to call it, we have saturation condition, right? So here we have saturation condition, but it's for a mixture of liquid and vapor, right? The same is true here, the same is true here, the same is true, and this 3 is actually on the line. Okay, so we have the properties for S1 and H1, right? And we also have the properties for S3 and H3. full liquid, full vapor, 100% vapor. What is the condition here? If you take a look at here, you can see the energy level hasn't changed. The only thing that has changed is the vapor quality, the amount of vapor we have in the system. So the entropy of this third location is going to be equal to the entropy of liquid, just the liquid part of state 2. Does it make sense? Yes? Yes?
You add that to the entropy of the gas at state 1?
No, because you have lost some energy there. Right? The energy level has changed. Temperature is not constant over there. So you can only do that between station 2 and station 3, or this point and station 1. Right? The energy level has to remain constant. Okay, let's go back to yes.
Why did you use the liquid and not the vapor? Why did you not use S1?
Because the energy level here, we are on the same energy level, right? So your liquid is actually has remained at the same condition. The only thing that is happening here is the phase change. Vapor is changing to liquid at the same temperature. So the entropy of liquid is going to be the same. So you are only adding more liquid to your mixture, right? And you're losing some vapor during this process, 2 to 3. Is it clear now? Okay. So,
On the axis.
what's that?
I think the confusion's on the axis.
T, temperature, and entropy.
Yeah, but if 2 and 3 are on the same Y line, or T line in this case, I think that's why some of those should be the same temperature, not the same.
It is the same temperature. Your okay. Entropy of the system. We actually that's okay. So entropy of station 2 is not equal to entropy of the liquid at station 2. It is very important. How do we calculate the entropy at station 2? It is going to be your vapor quality multiplied by the entropy of gas at the station 2, plus 1 minus your vapor quality, x, at entropy of liquid, at the station 2, right? Does this make sense? Entropy at the station 2 is the same, the total entropy at the station 2 is going to be the same as entropy at the station 1. That's the total entropy, the total entropy of the system. The only part that you are going to get from the previous entropy is the entropy of liquid. This part.
So you're saying right
Or you can actually let me rephrase that. Let's go back to the table. Let's go back to the table. The idea here is that between 2 and 3, the temperature is going to remain the same, right? Okay, and this is at saturation condition. The only thing that is changing is vapor quality. You are adding more liquid to your system. That's the idea here, right? So let's go back to that. That was 0.00 whatever megapascal, right? 0.08. This line. Your temperature is going to remain at 41.51, and you are going to remain at the saturation condition. So for point 2, you already have the entropy of the liquid part of your system and entropy of the gas part of your system. Right? You can read it from the table. You have it right here. Right? The only thing you don't have is the vapor quality. How much of your system is gas? Right? How much of that expansion in the turbine, or how much phase change that expansion has caused? Is this a little more clear now? We have it on the table, right? Temperature hasn't changed. Your saturation temperature and pressure hasn't changed, right? So that's, you have it. You have already read it from the table. Pardon me?
The vapor quality?
Not the vapor. How do you write the vapor quality?
Yeah.
Okay. So you read the entropies, right? And the process between a station 1 and a station 2 is isentropic, right? Yes.
No, I was just trying to figure it out in my mind, trying to imagine.
Oh, okay. I thought you had a question. That's all right. Okay, so we have, so we can actually, we can actually read the entropy of gas at station 2. We can also read the entropy of liquid at station 2, which is going to be using the information of a station 3, right? Again, because the only thing that is changing between a station 2 and a station 3 is the amount of vapor you have in your system. It's going to go from 75% to 0, right? Or 60% to 0. And that's the thing we need to calculate. But the total entropy of the system after the turbine has remained constant, which means that this S2 is going to be equal to S1. So we have SG, we have SL, and we also have S2. Based on this, we can calculate X. Is this clear? Do you remember this from your thermo, or you did not go over it at all? You did not go over it at all.
It was a long time ago.
I just get my crisscross.
Yeah, this.
You didn't go over this at all? One by one, I can't hear all of you.
Yes.
You went over it,
It's coming back.
coming back, but you didn't go over it. Who was your teacher?
Reynolds.
Reynolds, yeah. Yeah, Reynolds will definitely go over it. From the people who were not with Reynolds, Cyrus and Ben. You went, you talked.
It's like the quality, and it gives the quality and the next one.
Yeah.
I didn't take it back to find the quality. And we were always given that.
Okay, okay,
Yeah. This makes sense now.
okay. Does it make sense to everyone?
Yes.
100%? I mean, it can be 90%, 80%. As long as it's higher than 50%, I'm fine.
My issue is I just get mixed up a lot. I just need to kind of figure it out.
Yeah, okay.
It's been 2 years since we did it well.
Yeah, but so these are some, if you end up in the propulsion part of aerospace industry, you need to understand this very well. Okay, so we can find the vapor quality, but we still don't have the enthalpy at the state 2. How can we find enthalpy? The same formula, X H G2 plus 1 minus X H L2. Right? We can read the H and G and L from the tables. We have calculated X. We can find H2. So we have H1, H2, and H3 at this point. Brayton cycles, gas cycles are actually a little easier because we don't really have any phase change in them.
Yeah.
Okay. What's that? That's nice. Okay. But you have to answer a Rankine cycle question in your exam anyways. So I don't know how nice is that. But okay. Let's go to the debate. Let me ask you just to make sure you understand this. Is there anyone who can tell me what is this variable here? HFG.
Isn't that along with the curve point? Or if it's HF, the saturation is right?
But let's just really, since we don't have enough time, let's let go of the discussion. HFG is HF minus HG, right? And you can actually, it is defined as something that is going to help you with this equation, because if you do this xg And if you expand this, you're going to get HL2 minus X HL2. You can get these together, and H2 is going to be HL2 plus X multiplied by Hg2 minus HL2, which is the negative HFG, and H2 is going to be equal to HL2 minus X HFG. So you can simplify that equation. I don't know how much it helped, the simplification of it, but you just know that this is out there, HFG. Okay, so we still have, yes.
Where do you use HFG for?
Exactly this. I mean, it's not just, that's the enthalpy of evaporation, right? So if you want to find the total heat during evaporation, or the name escaped me. They have sensible heat, and also what's the other type of heat?
That's HL2 minus X HL3.
That's right. That's right. Yeah, so the heat of evaporation, yes. What's that? So enthalpy is the amount of energy in your system, right? But entropy is a totally different thing. It's the amount of randomness in your system. When you have higher entropy, you have higher, your system is going to be a little more random. Not between the boiler and turbine. The entropy is going to remain constant between state 1 and 2. So inside the turbine, because we have an isotropic process, which is a reversible adiabatic process. A reversible process is a process at which entropy does not change. Okay?
So the process, oh, you said the entropy doesn't change the process. I thought you said
No, entropy. Enthalpy does change. Entropy. S. Okay, so how can we calculate the enthalpy at station 4? Same way. But let's look at this plot here. Between a station, we have the enthalpy at station 1, station 2, and station 3 now. But between station 4 and 1, there are some parts of it that we are just heating water inside the boiler, right? There is no phase change. So vapor quality, so you can't really use that. You can't really use vapor quality analysis. If you use the vapor quality, yes.
Is there a pressure associated with that?
Pressure associated with pump. Are we given a pressure with pump?
No, I guess we're not, but like another table or something.
Another table. What is the other table?
I think that like the superheated stuff confused now. Actually,
What's that?
I'm just getting the superheated steams confused now.
We are not there yet. We'll get there, but we are not there. Okay, any ideas? Think about it. Yes.
It is the mass flow rate equation that we have, where it's LP equals mass flow rate of H4 minus H3, knowing all the variables.
H4, but do we have WP though? And we also don't have M dot.
I thought we had mass flow rate.
We don't have that. Do we? No. I guess we have to continue this in the next lecture because we are already at T3:35. And Okay, so I wanted to finish this part in one lecture, but I guess we need a little more review of thermodynamics, so we're gonna like take our time here. It doesn't really. We may need to skip through some parts of combustion, which is all right. We have a full another course of combustion you can always take, and yeah.